Hello everyone, and welcome to the OneClass channel. My name is Jeff Krause. I have a PhD in physical chemistry, and today I'm going to run through a few undergraduate level, high school level physics questions. So we can get right started here. So this first question says, we have a disk. We have a disk rotating with a moment of inertia of 100 kilograms. I must have selected some extra wide thing here. So I have a disk with a moment of inertia of 100 kilograms meters squared, and it's free to rotate without friction about a fixed axis through its center. And we have some tangential force which can act, and the force can take on anywhere between 0 to 50 newtons, and it can be applied anywhere between 0 to 3 meters. So we can apply the force anywhere we want along the radius of the disk. And we need to find a pair of values such that we move a delta theta equals 2 revolutions in a time of 1 second. Okay, so we're given all this, and it asks if the answer is unique. So we're given a force that acts at a radius. So what we're really given is a torque, as torque is F cross R, where R is the radius. But we can simplify this cross product by writing this as just F R sine theta, where theta is the angle which it's acting. As it's tangential, it's 90 degrees, so this angle is 90 degrees. The sine of 90 is 1, and so this is just the force times the radius. Okay, so we have some FR, and I'm going to actually write it as FR to be consistent with the notation I used above. So we've got some force times some radius, which is our torque. In circular motion, our analog to our force equation is just that our sum of our torques is equal to our I alpha. And I'm going to keep using this vector notation, even though I don't really have I guess I'll put an n hat, just to give it our direction, and in this case, the way I've drawn it, right, we would use a right-hand rule and actually say that this is, if we draw our force, not that the direction really matters here, but just to be consistent, and our radius, then we would have our fingers going towards the direction of the force, and we would point our palm towards the direction of R, and this hand is disfigured, but it's okay. And then the thumb would point in the direction of the unit vector n. So the way I've drawn it in this figure here is correct. So our motion would be counterclockwise, and so the direction would be upward. Or in this figure here, the torque unit vector would be out of the page. So that's really mostly an aside, but just for directionality purposes. But we're going to drop the n hat from here out just because it isn't necessary, as our alpha is also going to be an n hat, so we can just solve for the magnitudes. Okay, so the sum of our torque is just Fr, and it's going to be equal to our I alpha. We're given our I, and we're asked to solve for F and R. And we're not asked to solve for an alpha, we're actually asked to solve for a theta, but we can do that. So first of all, though, we're going to solve this for alpha. Now alpha is d omega by dt, and so that means we can rearrange this to say that d omega is alpha dt, or we can integrate both sides to get our omega. So integrating the omega side, we would have omega minus omega naught. And then the alpha side would be the integral of Fr over I dt from 0 to t. Assuming that we're starting from time 0 and going to some time t. In this case, we're just going to use, I'm going to leave it as t for now, even though in the question it's given 1 second. But the question is also tells us that we start from rest, so that's 0. And so omega is Fr over I, as these are going to come out of the integral, times t. Minus 0, I should say, as we're going from 0 to t, but of course 0 is 0. So then it's just Fr over I t. Now we can solve for theta, as omega is d theta by dt, and so then d theta is omega dt. So we can integrate both sides. From this one goes from theta naught to theta, and this goes from 0 to t as well. And so we have a theta minus theta naught is equal to the integral from 0 to t, Fr over I t dt. The integral of t is t squared over 2. And this is going to go from 0 to t. But of course, when t is equal to 0, this whole thing goes to 0. So then this is just Fr over I t squared over 2. And then now we have our delta theta. So our delta theta is equal to Fr over I t squared over 2. Okay, so now we have everything we need. So just to reiterate, right, our I is 100 kilograms meters squared. Our t is 1 second. And our delta theta is 2.0 revolutions, which is equal to 2.0. Actually, I'm not going to write it like that, because that's just going to be a lot of rewriting. So we want to convert this into radians, so we're going to multiply by 2 pi rads per revolution. And so this is then 4.0 pi. I'm just going to leave it like that. Okay, so now we can pick say a value of force and get and then we can solve for the radius. So if we pick say F equals 50 newtons, then what we would actually find is that our radius is not big enough. So we would find that R is delta theta times I, 2 times delta theta times I over F, which comes out to be, subbing in our values, about 800 pi kilogram meters squared per second squared, all over 50 newtons. And if you do that out, this R is well greater than 3 meters. And as this is our biggest value of force, that is going to be our smallest radius, which means that, at least for the values given in the question, there are no values of force or radius that work. But if we take a look at the solution here that somebody wrote up, they use 10 seconds. And 10 seconds is possible, so I'm going to do that. So I'm going to use t equals 10 seconds. As the t equals 1 second there's no force or radius that works. So if that's the point of the question, then fine, there's just no values of force or radius that work. But for the point of having something to solve, I'm going to use 10 seconds. And so then our radius would be 2 times delta theta times I over F, which is equal to, and I missed my delta t, which should have been down here, so t squared. And so that would have only been 1. That would have been the second squared actually here. And I'm going to just get rid of that. So that would have just been the 1 there. So then now this is equal to 800 pi kilograms meters squared over 50 newtons, and put my t squared, times 10 seconds squared. Or that could have been 100 seconds squared, but if we run this through our calculator, then we get 0.503 meters. And so then we have a pair now, so force equals 50 newtons, can act at an R of 0.503 meters. Or if we pick an R of, say, 3 meters, then we can rearrange this for force. Which would be 800 pi kilogram meters squared over 3 meters times 10 seconds squared, which comes out to be a force of 8.38 newtons. And so we have another pair. And so obviously from just solving it the 2 times, neither of these are unique solutions. And in the end, you would actually have an infinite number of solutions because you could pick any value. and find an R for it. Obviously, these are the borders, so you could actually only pick values between 8.38 to 50 newtons, or R's between 0.503 to 3 meters. Anything less than those values would be too small. So the force would have to be too large, or the radius would have to be too large. Okay. But there's still an infinite number of solutions between those values. Okay, if we check the solution here, so I guess we're pretty sure that this is going to be good since I followed the time they used. And yep, so they basically run through the same process. So rather than doing the integrals, they just directly use the equation, but that's fine. You can you rearrange for alpha and then just plug in your values. So they have the same thing here. So I alpha. So the alpha comes from 2 times delta theta over, and they didn't multiply by the I, right? So 2 times delta theta is this, or this delta theta is 12.57 rads. I left that as pi, 4 pi, but you can imagine that 4 times 3 comes up to be about 12. Okay, and so then, and they chose force values of 25.1 and an R of 2. So, so they have even another couple values that you could pick from. So obviously, it's becoming more obvious, at least, that the solution's not unique. So the solution is correct. The posted question is an error, I believe. T equals 1 second. T equals 1 second is not, has no solutions. All right. So it looks good. So this just says inertia of a disk. So I'm going to solve through a couple different ways of getting the moment of inertia for a disk. So the most common would be the moment of inertia about an axis which goes through its center and is perpendicular to the disk. So the moment of inertia for a solid mass object is going to be the integral of r squared dm. And so the trick here is identifying your dm. So what we do in the disk case is identify some small area. We need to have our mass defined. And so if our mass is its density times its area, where in the case of a disk, that would be rho times pi r squared, where r is its outer radius. Then we can identify a small mass term at some radius r, having some thickness dr, and we can visualize this by extending out. So essentially taking this circle, pulling it out, and then cutting it and laying it flat. And so it would have some radius or some thickness dr, and its length, because it's a circle, would be 2 pi r. And so then its area would be, so a small area would be 2 pi r dr, and its mass would be rho dA, which is just rho times 2 pi r dr. And so then there are our small units of mass, right? And so then now we have everything in place to plug into our mode of inertia equation. So r squared dm, which is then integral r squared rho 2 pi r dr from 0 to r. And we can bring out the constant terms, so 2 pi rho, and then integral from 0 to r cubed dr. So the integral of r cubed, with a power, you always put up the power by 1 and divide by the value. So then it's 2 pi rho r to the 4th over 4 from 0 to r. And then when it's 0, it's going to be completely 0, so we just really need the top solution. So 2 pi rho r to the 4th over 4, or pi rho r to the 4th over 2. And then we can make one more simplification here. So our mass, we said, was rho pi r squared. If we look over here, we have a rho, a pi, and an r to the 4th. So we can take these terms out and say that this is our mass, r to the squared over 2. Okay, so it's just mr squared over 2. So that's simple. But moment of inertia depends on your axis system choice. So if we say swap the axis and instead use that one, which goes through its center, even though it doesn't look like it does. I'm just going to redraw that so that it doesn't look like I'm trying to do something crazy. And I don't know if that was any better, but all right. We're going to do an axis that's perpendicular, or that lies in the plane of the disk and goes through its center. So again, here the trick is identifying your small mass segment. And so remember that we're dealing with perpendicular r's. So now the small mass segment has to be a straight line. And now I'm just going to expand that a bit. And so if we look at just the half of the circle, then our r's are going to go from, are just going to be these lines, and we need to sum them all up. Another way of representing it, though, is by theta, and that turns out to actually be the easier way to solve this. And so that's our r. If we define some theta, then if we look, these hypotenuses here are radii, and so this here is r cos theta, which means that this length, this line segment that I have here, which would have a radius of dr, or a thickness of dr, sorry, the length of it is going to be 2r cos theta. But what's dr? Well, if we look, r is r sine theta, and we can actually define dr through differentiation here. So dr is then r cos theta d theta. And now our area segment, which as we defined previously, but our area segment now is just the length times the width, which is going to be 2r squared. I'll just write it all out, actually. So 2r cos theta times dr, but dr is this. So r cos theta d theta, which is then 2r squared cos squared theta d theta. And so that's our area segment. And so our mass, just as previous, is going to be rho times our area segment, which is then 2 rho r squared cos squared theta d theta. And now our moment of inertia is integral r squared dm. We're going to use this definition of r. So integral r squared sine squared theta times our dm, which is 2 rho r squared cos squared theta d theta. And we're going to integrate from 0 to pi over 2, because I already included both sides of the semicircle here. So we just need to go up to pi over 2, so just a quarter of the circle, and that encompasses both sides of the half. But now if we look, I'm only doing half of the disk. So to get the other half of the disk, we just need to multiply this by 2. So our moment of inertia is going to be 2 times this integral from 0 to pi over 2 of all these terms. And now pulling out all of our constants, and in this case our capital R is our constants. So we've got 4 rho r to the 4th integral 0 to pi over 2 sine squared theta cos squared theta d theta. Now this guy is not something that I know how to solve right offhand, so I just used an integrator. I looked it up online to get the indefinite integral. And so this comes out to 1 over 32 times 4 theta minus sine of 4 theta from 0 to pi over 2. And now we can do this all out fully, but if we look, right, if we put a pi over 2 in here, then this actually has a value. So 1 over 32 times 4 times pi over 2. Now if we plug in a pi over 2 into sine of 4 pi, well, that's sine of 2 pi. Sine of 2 pi is 0, so that goes to 0. And then if we plug in a 0 into either of these values, that's 0. So this is the only term that survives. And so just for simplification, I'm just going to use that term. I said that, but now I'm thinking might as well just do it. So I'm just going to do sine of 4 times pi over 2. And then minus 1 over 32. 4 times 0 minus sine of 4 times 0. So just to write it out, so this is sine of 4 times pi over 2, which is sine of 2 pi, which is 0. That's 0. And sine of 0 is 0. So those terms all go to 0. Okay, so then all we're left with is this term. So we can pull the 4 out, or, well, I guess we're just multiplying everything together anyway. So 4 times 4 is 16. Rho r to the 4th, and we've got a pi. And then we're dividing by 32 times 2, which is 64. 16 over 64 is 1 over 4. So that's rho r to the 4th pi over 4. And if we remember, our mass is rho pi r squared. So then this is just mr squared over 4. And so then there's our moment of inertia for a disk rotating about an axis which lies in the plane of the disk and goes through its center. So it's different because it depends on which axis you choose. And it takes a bit more work than the other kind, but not too much. Okay, so there's our two of the moments of inertia. Obviously, you could define an almost infinite array of axes, but there's a couple of the most common ones. If we look at the solution given here, we have the most common one, which is the axis which is perpendicular, so a half mr squared. So I would say that's still correct. So the moment of inertia for axis in the plane is mr squared over 4. Others are possible. And they can actually be derived from those as well, but that's for a different lesson. Okay, or this lesson in fact. So starting with the moment of inertia for a rod rotated around an axis through one end. So if we have a rod and it has some length L, it gives us that the moment of inertia about this axis is ml squared over 3. And it wants us to prove that the moment of inertia rotating through its center and perpendicular to its length is ml squared over 12. So we can just do the same trick as I have in a previous lesson and use that I is the integral of r squared dm and then start summing up masses. We can also use a kind of nifty little trick here. So armed with the moment of inertia about its center of mass, so that would be the middle, we can find the moment of inertia about any other axis system by just adding md squared, where d here is whatever distance we're moving in. So in this case, our d would be L over 2. Now we're given the moment of inertia about this axis and asked to find the moment of inertia about its center of mass. So we would rearrange this. So our center of mass inertia would then be the I we're given minus md squared. So the moment of inertia we're given is ml squared over 3 minus m, and that's L over 2 squared, which is ml squared over 3 minus ml squared over 4, just expanding the square. Now we need to give these this same denominator, so we need to multiply this by 4 and multiply this, or 4 over 4 I should say, and then multiply this by 3 over 3. And so then this is 4 ml squared over 12 minus 3 ml squared over 12, which is equal to ml squared over 12. And so the moment of inertia about its center of mass is ml squared over 12. which is what it asked us to show. So that looks good. So again, just to reiterate this this equation here, that means that if you have the moment of inertia about an axis which passes through its center of mass, you can find the moment of inertia about any axis which is parallel to that by just adding md squared. So you can easily translate any mode of inertia with that equation. Okay. So the solution here does the normal thing and sums up little dm's. So that's handy as well. So we can define our dm and go through and find the moment of inertia as the integral of dm r squared. And then with their definition, they get the moment of inertia for the rod from one end is ml squared over 3, which was given in the question. And then for an axis which passes through its center, then we're going to just integrate from minus L over 2 to L over 2, which gives us our ml squared over 12. So the solution is correct. But it's solvable with the equation I gave here. Okay. Okay, so this is a spring question. And this is a fairly simple one, but warrants some explanation. So if we have a mass on a spring, then its frequency is given by square root of k over m, and its period is then given by 2 pi over omega. Or another way of saying is that our omega is 2 pi over its period, which we can then solve for the period. And the question's asking if we increase the mass, will it increase its vibrational period? So to answer this, the best way is just to consider the equations we have here. So here's our omega, so we can sub in. So 1 over omega is just root m over k, so we just swap the two. And so our period is directly related to the square root of its mass. And so that means that if we increase the mass, then we will definitely increase the period. And so that's true. So increasing the mass will increase the vibrational period. So if we check the solution here, our period of vibration comes out to 2 pi root m over k, which is correct. So then our period is directly proportional to the mass. So if the mass is increased, then we increase the period. So that's true. That's good. And so that looks correct. Okay, so we have a certain spring that obeys Hooke's law. So Hooke's law is F equals minus K delta X. The work done in stretching the spring by 10 centimeters is 4 joules. So now we're talking about energy. So our energy our energy is then, or potential energy, I should say, our potential energy is 1/2 kx squared. And this comes from the fact that our potential energy is minus integral of force dx, where in this case we would use x in here, not delta x, but it's just assumed known that this is our delta x. Okay, and so if we integrate this expression, we will get a half kx squared. Okay, so if we want to increase our energy or if we increase our x by 10 centimeters, then we're increasing our energy by 4 joules. Or another way of saying this is that 4 joules is a half k times 10 centimeters squared. Now, I guess this assumes that we're starting from x naught, but we don't need to, because in essence what this expression is telling us is that for every x we move, we increase our energy by a squared amount. But in any case, we can leave this like this. And so how much additional work is required to stretch the spring an additional 10 centimeters? So if we want to know now our energy for this, given this, well, we can solve for our k by saying that it's 8 joules over 10 centimeters squared, or plugging this in, we would have 4 joules over 10 centimeters squared. I shouldn't have taken those out. So this is doing it quite simply without running anything through a calculator yet. And so then this is 4 joules times 20 over 10 squared, which is 4 joules times 2 squared. Right, because 20 over 10 is just 2. And so if we double our distance, then we multiply the energy by 4. And so that's kind of that's really the takeaway here. Or we square whatever the factor is that we're adding. And so it would be 16 joules. But the question asks how much additional work. Right, so in stretching it to 10 centimeters, we did 4 joules. In stretching it to 20 centimeters, which, sure, that's double, let's go with that, is 16 joules. So the additional work is just in here. So that would just be 16 joules minus 4 joules, which is then 12 joules. So there's 12 joules of additional work. Okay. So yeah, so we could calculate the k and get an actual value, which is done in the solution here. And then we could just plug it in to get our total work to get to 20 centimeters, but then the additional work is then just 12 minus 16 minus the 4, sorry, which gives us our 12 joules. So that looks good. right. All right. Okay, so we've got I'm just going to draw the figure here. So we've got a horizontal beam and a wire which extends down and supports a drum. And the beam is 4 meters long. It's attached to a wall. This height is 3 meters. The length of the wire is 5 meters. And the drum weighs 300 newtons. The beam weighs 200 newtons. And the question asks, what is the tension in the wire? Okay. So when we're given a question like this, where we have forces acting in various directions, and particularly in different points, then it's easier to use, oh yeah, I suppose, this is on a hinged pivot as well, because otherwise that wouldn't work. So this is on a hinged pivot, meaning that this beam is free to move up and down, but at present it's stationary. So when we have something like this, the easiest way is to use torques, not forces. So we can use the sum of our torques is equal to I alpha, where I'm using a vectorial notation here, because we will want to pay attention to direction. Although for the most part, the direction is either going to be out of the page or into the page. And we're going to define that using our right-hand rule. So we've got 3 torques here. The 1, 2, and 3. Okay, so our torque 1 is F cross R. And it is perpendicular, and the direction is going to be, you point your fingers of your right hand towards the force, your palm goes towards the radius, and then your thumb points in the direction of the torque. So in this case, the torque would be out of the page, so we're calling this a positive torque. So then this would just be 200 newtons times, and it acts at the center of mass, so that would be 2 meters along the beam, so 400 newton meters. Now our torque 2 is again F cross R, so this would be the barrel. It acts perpendicularly as well. It's down at the end of the rod, so then this is, and if we look at the direction, it's downward, the radius is right, and so the torque is out of the page again, and we're defining that positively. So it's just FR, and because it's perpendicular, the sine of theta is 1. And so this is 300 Newton meters. And again, it's positive as it's coming out of the page. Okay. 300 newtons times 4 meters, because it was acting at the end, so that would actually be 1200 Newton meters. That would be a slightly different answer. And now to look at the third torque, I'm just going to draw it so that we can see it. It's the tension, and here's our R. And so now if we point our fingers towards the tension, and our palm toward in the direction of the radius. So that would be this way. Our thumb would point downward or into the page. And so this is a negative torque. And my strange hands everywhere, but I hope if you follow along and this makes any sense. Okay, so then our torque 3 is F cross R, which is our tension, times our 4 meters, times the sine of theta. That was the other reason why I wanted to draw this, but then I muddled it up. So this is our theta, as we join them end to end to get our theta. Now, the tension normally is actually acting at the end here, and that's the theta we would be given. And if we look, these are similar triangles. Okay. I'm going to re-sketch the figure just to make this even more obvious. So we've got a triangle like this. Our tension is acting this way. So there's our sketched tension at joined end to end. So that angle and that angle are the same. We're given that this is 3 meters, this is 5 meters, and this is 4 meters. So this angle, theta, is, this angle, I'm going to call it actually phi, just so that I'm not getting things all confused. This angle phi, or I should say the sine of phi, is the opposite over adjacent, so 3 over 5. Now this angle, theta, which is what's here, which is what's in our tension expression, if we look, sine of theta is equal to sine of, so the full angle is 180, so that's 180 minus phi. But we can use our laws for sine here and say that sine of theta is just equal to sine of phi, because sine of 180 minus phi is just sine of phi. And so then that equals 3/5 from this expression. And so then that simplifies our torque 3 quite a lot, because that means that our torque 3 then is just the tension times 4 meters times 3 over 5. And so now we're in a position to use our sum of our torques, right? So as we said, this is actually a negative. So these all should be negative. We went through all that effort to get directionality, so that will be negative. And so now the sum of our torques will equal our I alpha, but nothing's moving, so that equals 0. So the sum of our torques will be 0. So now summing up all our torques is equal to torque 1 plus torque 2 plus torque 3. And I'm just including the vector, but we're not going to bother with the any unit vectors, but we are going to bother with sine. So our first torque was positive, which was 400 Newton meters. Our second torque was also positive and was 1200 Newton meters. And our third torque was negative and was equal to the tension times 4 meters times 3 over 5. And then that all equals 0. And so now we can solve And that shouldn't have been a tau, but a t, because that's our tension. Now we can solve for our tension by summing this up and rearranging. So we have 1600 Newton meters is equal to the tension times 4 meters times 3/5. So our tension is 1600 Newton meters over 4 meters times 5/3, which just equals 666.67 newtons. Okay, so now if we check the solution here, so we need to sum over all of our torques. 200 times 2 plus 300 times 4 is equal to, so that's where it came out in the end, right? So that's 1600 is equal to 4 times 3/5 times the tension. So here we have exactly the same thing. And then here they get that the tension is 800, which is just wrong. They just made a calculator error. So there's a calculator error at final solution. Should be T equals 666.67 newtons. So I guess it's incorrect, but everything else is correct. Okay, this question here asks, so we've got two charges, 3 nanocoulombs, a distance r from the center, and then another distance r to another 3 nanocoulomb. And then that's a distance r from this point. So it asks, what is the electric field due to these charges at that point? So electric field is a vector, so we want to set up an axis system. I'm going to pick my origin here and have x and y. So our electric field is given by 1/4 pi epsilon naught, the charge over the distance squared times r hat. So r hat being the unit vector in the direction. So for and we have two charges, 1 and 2. So then we can get two electric fields, and then our total would be the sum. So for E1, we would have 1/4 pi epsilon naught Q over R1 squared R1 hat. Looking at the figure, our R1 hat, or our R1 vector, from this position is minus r x hat minus r y hat, and our R2 vector is minus r x hat plus r y hat. So these are from the positions of the charges, not from the origin. And so we can solve for our magnitude, which would be the square root of r squared plus r squared. So that's summing the individual squared components. And that would be square root of 2r. And then our r1 hat is just our vector over our magnitude, which is then just minus 1/√2 x hat minus 1/√2 y hat. And similarly, our 2 magnitude is √2r as well, and our r2 hat is minus 1/√2 x hat plus 1/√2 y hat. So now we're in position to solve for our individual electric fields. So our E1 is just 1 over 4 pi epsilon naught, 3.0 nanocoulombs over root 2 r squared times minus 1 over root 2 x hat minus 1 over root 2 y hat. And our E2 is 1 over 4 pi epsilon naught, 3.0 nanocoulombs, root 2r squared, minus 1 over root 2 x hat, plus 1 over root 2 y hat. Now our total is just the sum, which is then we just add these up. So we're going to pull out the like terms, which is all this stuff. 3 nanocoulombs. I'm going to go ahead and square this so we get a 2r squared. And then the vectors are going to add up. So 1 over root 2 x hat minus 1 over root 2 y hat minus 1 over root 2 x hat plus 1 over root 2 y hat. And now obviously the minus here and the plus here are going to cancel, and the x hat will double up. So 1 over 4 pi epsilon naught, 3 nanocoulombs over 2r squared, and then we'll get a minus 2 over root 2 x hat. Go ahead and cancel this 2. And we could probably pull out some more numbers, but since everything's still in R, I'm just going to leave most of it. And so we get minus 3.0 nanocoulombs over 4 pi epsilon naught root 2 r squared x hat. Here, this looks good. They did go through and figure out all the numbers, which you could do, but since everything's still in R, I think that's fine. And so the magnitude is just the unsigned value, and the direction is in minus x, or from the figure towards the left. And so this looks good, so the solution is correct. Okay. And I'm gonna cut that there and say that's good for today. I hope you enjoyed this session. If you did, please subscribe to OneClass. If you want to leave questions, please follow the links provided below. This has been Jeff Krause